Hello physics students, in this short video I want to go over the answer key to the practice quiz for Unit 5 Energy Transformations. And there's a few things I want to point out in this. The key is posted after you submit the work for the practice test itself, and then you can unlock this and see the key. What I want to do is I want to focus on just a few of these problems. For the first one, when you're doing work, one of the big ideas in this unit is that the work done and the distance have to be in the same direction. And so obviously there are three distances they give you in this problem, but only the vertical distance is used because we're doing work against gravity, so therefore the force is a vertical force. So those two have to line up, vertical, vertical, work is force times distance. So you always keep that in mind, and then power, of course, is work divided by time. These two are kind of level 1 questions, and I hope everybody gets these, and they're really the basic ideas of the unit. Another one like that, kind of a level 1 question, are these ideas with energy transformation between kinetic and potential. So in this case, Tarzan is swinging on a vine, swings down, and we want to know the velocity that Tarzan has at the bottom, so Jane can match that and get caught at the same time. So we want to set this up that potential energy at the top is equal to kinetic energy at the bottom, and then solving through. Notice I did set this up just algebraically at first. You might do it that way, you might not, but those are some things that I've been trying to encourage, because you know that when that does happen, a lot of times terms drop away. Like in this case, mass shows up on both sides, so we can cancel that out. And then our final velocity is the 19.8 meters per second. Okay, a slightly more difficult one when we're talking about energy transformations will be ones where you have combinations of energy together, and we have to be careful about where the situation is and what type of energy is happening at that moment. So you can always break these problems down into smaller moments in time. When we're talking about this sliding for donuts, imagine you have across the floor kind of a track, and there's a surface that the object, in this case the donut, would slide on, and at the start of the track there's a launcher, and the launcher has a rubber band that's stretched backwards. So it's going to store in energy as the farther you stretch the rubber band back. It's storing in potential energy. It's also doing work. And the amount of potential energy that gets stored into the rubber band is then transferred into kinetic energy after that object is released, and then the object slides to a stop, and then that energy that was kinetic is now going to be equal to the work done by friction to stop that object. All right, so those are the energy transformations to kind of consider. And so when we look at a problem like this, we're going to see that there's potential energy stored in the rubber band, converts to the work done by friction in order to stop. And so those are the things that we're going to look at, kind of that beginning potential and the end work done by friction. Now I can use what they've given me, where we want to solve for how far back you have to pull the rubber band, or that x in the 1/2 kx squared, knowing that the amount of force of friction was given times the distance that friction force was applied. Okay, now sometimes they won't give you the friction force, but they'll tell you like a coefficient, so you can solve for the friction force knowing maybe the normal force, things like that. But just keep that in mind, that we're always setting up this energy relationship, and that drives what we're going to do next. Okay, so when you solve that out, that distance stretched back should be about 11.45 centimeters or 0.1145 meters. Okay, another one that's a little bit more on the kind of moderate side would be a problem like this, where you have to talk about total energy, where you're adding the kinetic and potential to the top. And I know, yes, it has potential because of their height, but also because the kid is moving, they have some kinetic energy as well. Those combine together to give you the total energy of the system that will then stay the same all the way through the path, and so they'll have the same total energy when it comes to a stop at the other hill. Okay, in this case there's no friction, so we don't have to worry about some of that energy being converted to thermal energy, but the total energy remains the same regardless. Even if some of it is converted into thermal, you'll just have less potential, so it won't go quite as high as it started on the one side of the ramp. All right, so you can see here, once we figure that out, we'll add our potential and kinetic together, get our answer in joules, and then use that down here to help us find the velocity, because we want to know at the bottom where their height is 0, there's no potential anymore, so all that energy is converted into kinetic. So all the total is kinetic, and then we can solve for our V. Okay, so those are the things we're going to take a look at. And then if we want to find the maximum height, now notice the kit starts at 4 meters. If there was only potential in the beginning, his height over here should also be 4 meters. However, there is some extra energy from his velocity, his kinetic energy, that will extend his distance up here beyond 4 meters. And that is why when we do this, we want to make sure we add in the amount of potential energy at the top is equal to mass times gravity times height when he comes to stop eventually, but we're using the total energy in the beginning, the potential plus the kinetic. And that's why this height is more than the 4 meters that he would have if he only started with potential. All right, hopefully that makes sense. If not, please reach out and we can go over that in a little bit more detail. All right, one of these bullet questions is another kind of upper level question. It's one of my favorites. I love these because it helps you illustrate how powerful these energy equations are and what you can solve with them, knowing how these energy transformations work. And so the idea is a bullet's flying through the air, has a certain velocity, hits a tree, gets lodged in the tree, and we want to know how much force it takes to stop that bullet. So in other words, we want to know the work done by the tree to stop the bullet, the amount of force times distance. Well, we know the distance. All we need to do is solve for the force using our energy relationship where KE is equal to the work done to stop the bullet. So the kinetic energy the bullet had in the beginning, flying through the air, will then equal the amount of work done by the tree in order to stop the bullet. So that's the force to stop times the distance. We're solving for that force. Plugging in the other values that we have, we end up with a force of about 10,125 newtons. Okay, like I said, this is a cool application because this would be a hard problem to solve if we didn't have that work energy theorem to use to solve these out. All right, one last thing. This is another extension, but we can also come back to equations that we've done in the past. And so maybe we want to know how long it takes between the time that bullet enters the tree and it stops. So we know the initial velocity is 450, the final velocity is 0. We don't know the acceleration to help us find the time, but we do know that the force acting on the bullet is a uniform force. So it's going to have a uniform acceleration, and in this case we could use that force we just calculated divided by the mass of the bullet to figure out what that acceleration is. It's a huge number. Doesn't really matter how big it is, but we can put that into our equations to solve for time, and we end up with a really small amount of time, which makes sense. The bullet's going to stop really quickly. All right. Once again, easier to do with energy than it might be to do with purely kinematics. All right. Another question that is an extension with kinematics and energy is this last one. So the arrow is shot straight up in the air. We want to know how much work is done to pull the arrow back, so we can calculate that by the force applied to the arrow and its distance. And then know this energy relationship where the work done to stretch the bow back is equal to the stored potential energy and is equal to the kinetic energy when it's released. That's key, at the release point. So then the work done is equal to 1/2 mv squared, which is the kinetic energy at the release. This would be how fast it's going initially if we solve for V. Pretty cool. Now I can use that answer and know that at the top of the journey, it will change from that kinetic energy into potential. So once I could put in the 113.75 joules here, or because I don't know necessarily the mass of the arrow, I could just set it up so the potential energy in the beginning equals the kinetic energy, or sorry, potential energy at the top equals the kinetic energy in the beginning, and then cancel the mass out. All right, now to find this, actually we will need to know the mass a little bit. So I will add this in. I just use a 65 gram arrow, which was 0.065 kilograms. We needed that to find out what this velocity was. So that wasn't given and it should have been. So I'm going to add that in, of course, into the description. So make sure, hopefully you read that. And then as we're going through the final velocity and the time, we can just use our kinematic equations again, knowing that our speed at the beginning and our speed at the top is 0. And then the acceleration, since it's just a projectile, is the acceleration of gravity. All right, times 2, because we want to go up and down for a total time, and then we can get these answers right here. All right, so please reach out if you have some questions, but I just wanted to walk through those as a quick tutorial and be thinking about how you're building those energy equations in each of these different problems. So you're taking a look at where the energy is potential, where it is kinetic, and where work is done when you're faced with those scenarios. Like I said, please reach out if you have any questions, and have a great rest of your day.